What happens when construction crews no longer need air, sleep, or constant instructions? In this project, we'll explore robotic swarms that can scout, mine, build, and repair across the Moon, Mars, asteroids, and orbit, the next frontier for autonomous physical systems. We've moved from human-centered AI to bio-intelligent systems, and then into robotic swarms working in disasters, farms, oceans, and forests. Now that same autonomy moves into space, where distance, danger, and communication delays make local coordination, repair, mining, and construction essential. These swarms are the first construction crews for space, but without people in the danger zone. They scout terrain, identify useful minerals, and turn local material into building blocks. Specialized robots then divide the work. Some mine, some transport, some print habitats, assemble power systems, build landing pads, or repair what breaks. The key shift is autonomy. Instead of waiting for every command from Earth, the system coordinates locally and keeps progressing. By the time humans arrive, the basic tools of survival may already be in place. A swarm that works on the Moon will not automatically work on Mars, an asteroid, or in orbit. Each environment changes the design problem. The Moon favors early infrastructure and nearby resources. Mars adds distance, dust, and delayed control. Asteroids require anchoring and careful movement in microgravity. Orbit focuses on assembly, repair, and collision awareness. Adaptability is what allows one swarm architecture to stay useful across all of them. At this scale, the swarm is a mission system, not a set of separate robots. Scouts map terrain, identify hazards, locate useful resources, and recommend safe construction zones. Mining units extract regolith, ice, metals, and silicates. Builder robots turn those materials into habitat shells, landing pads, solar arrays, and other infrastructure. Repair units keep the system alive through inspection, fault response, and replacement parts. Coordination ties everything together, so each robot shares status, tasks, and discoveries. The real power comes from the loop between these capabilities. The swarm also works as a layered system. The physical layer does the work, moving, digging, anchoring, lifting, and assembling. The perception layer turns a harsh, unfamiliar surface into usable information through vision, LiDAR, radar, thermal sensing, and terrain models. The production layer converts local resources into useful outputs, from processed regolith to printed parts or extracted metals. Finally, the coordination layer keeps the operation aligned through AI planning, peer-to-peer communication, distributed records, and rugged edge computing. Resilience comes from these layers working together, even when Earth is far away. Computer vision gives the swarm a shared sense of the terrain. Stereo cameras, LiDAR, radar, thermal imaging, spectroscopy, and orbital data are fused into 3D maps showing shape, texture, temperature, and composition. AI turns those signals into decisions: which slopes are safe, which craters to avoid, where ice or minerals may exist, and whether a structure matches its design. When hazards appear, such as dust, rockfall, or unstable ground, rovers can reroute, recover, and update the mission plan without waiting for Earth. ICERU changes the economics of space construction. Instead of launching every brick, shield, tank, and beam from Earth, robotic swarms identify useful local resources, then excavate, process, refine, and assemble them into working infrastructure. Regolith can become bricks, landing pads, or protective habitat shells. Water ice is even more valuable. It supports crews and agriculture, adds radiation shielding, and can be split into hydrogen and oxygen for fuel. Asteroids extend the idea to metals and rare elements. The goal is a self-reinforcing production ecosystem, not a supply chain from Earth. In a distant construction mission, Earth should not be driving every rover like a remote control vehicle. Operators define intent. Build this pad, map this zone, preserve power reserves. The AI planner breaks that intent into tasks for individual robots, then schedules them around battery levels, system health, terrain risk, priorities, and communication windows. As robots work, sensor feedback updates progress and hazards. If one robot gets stuck or a route becomes unsafe, the swarm reallocates work locally. Humans stay in the loop, but mainly to set goals, approve exceptions, and monitor outcomes. Here, blockchain means a shared operational record, not speculation. Off-world teams may include rovers, habitats, satellites, and Earth-based partners, all working through delayed or intermittent links. A distributed mission ledger lets each agent record what it did, which resource was extracted, where a material batch came from, what repair was performed, and which task was completed. Smart contract logic can reserve power, grant permissions, or trigger milestones automatically. The value is trust under distance. Fewer single points of failure, stronger audit trails, and durable mission memory for science, insurance, replication, and collaboration. In a space swarm, edge computing is not just convenient. It is survival. Each rover needs enough onboard intelligence to see hazards, plan a route, diagnose faults, and coordinate with neighbors when Earth is minutes away or temporarily unreachable. That requires radiation-hardened, low-power hardware, compact AI models, and fault recovery by design. If one unit drops out, the swarm redistributes work and keeps moving, responding locally to dust storms, terrain failures, or solar events. Now bring the pieces together as a continuous feedback loop. Robots observe the terrain, locating safe paths, hazards, build sites, and useful deposits. AI turns that field data into assignments, balancing urgency, machine capability, energy, and local conditions. Resources are excavated, refined, and converted into printable material or modular parts. Construction robots build, inspect, and report results. Every action updates the mission record, including progress, maintenance, and material provenance. Humans supervise the loop, set intent, and intervene when priorities or risks change. Imagine an early lunar South Pole industrial zone. Swarms print habitats, shielding, storage, and utility structures so crews can stay longer. Nearby, other robots deploy solar fields, cables, batteries, and power relays. Mining units extract ice, recover metals, move material, and update resource maps. Manufacturing platforms then turn those inputs into spare parts and larger assemblies. The business opportunity is not one robot. It is the infrastructure layer that every future mission depends on. By 2050, the first real off-world workforce may not be astronauts. It may be swarms of robots arriving years ahead of them. On the moon, they could grade landing zones, assemble habitats, and maintain power grids. Around asteroids, they could extract materials for orbital factories. On Mars, they could prepare shelters, fuel systems, and resource processors. The big shift is from one-time exploration missions to durable industrial ecosystems that keep working between human visits. The big takeaway is that off-world autonomy is not one robot doing one task. It is an ecosystem. Scouts, miners, printers, builders, repair crews, planners, and edge computers coordinating as a swarm. By 2050, humans may arrive after the first infrastructure is already prepared. Next, we bring that same coordination logic back to Earth, into adaptive urban mobility.